the superposition of waves and pulses. That's what we're talking about right now. Ordinarily, you're going to have more than one wave arriving at any one point at the same time. You'll often hear two or more sounds at the same time. That means two or more sound waves from different sources are all arriving at your eardrum at the same time. We know that if one wave hits a little bit of mass in its path, that little bit will start to oscillate with the same period and frequency as the oscillation at the source of the wave. But what's going to happen if two or more waves hit a little bit of mass simultaneously? What's the displacement of that little bit of mass, displacement away from equilibrium of that little bit of mass going to look like? The answer to that is the principle of superposition. When several waves hit a little bit of mass simultaneously, the actual displacement away from equilibrium of that bit of that mass is the sum of the displacement you'd get if only the first wave hit, plus the displacement that you'd get if only the second wave hit, plus the displacement you'd get if only the third wave hit, and so forth. And let's illustrate that principle with a couple of pulses, similar than waves, a couple of pulses traveling in opposite directions along a string. Here's one pulse moving left to right at a speed of 1 centimeter per second, and at time 0, the pulse is sitting between x equals 0 and x equal 2 centimeters. And then here's another strange shaped pulse moving with the same speed but in the opposite direction. It's got a velocity of minus 1 centimeter per second. Both of these pulses have to have the same speed because they're both moving through the same medium. Speed of a wave or pulse depends on the medium, and if the medium is the same, the speed has to be the same. So let's think about what happens 3 seconds later. We know that in 1 second, each of these pulses moves 1 centimeter. So in 3 seconds, the front of this pulse has moved from 2 to 1, 2, 3, moved from 2 to 5. So, and then the back of this pulse has moved 3 centimeters in 3 seconds. 1, 2, 3, now it's at 3. So the triangular pulse is now right here between 3 and 5. It's moved 3 centimeters to the right. And this one will have moved 3 centimeters to the left. The front of the pulse will have moved from 7 to 4, and the back of the pulse will have moved from 10 to 7. So this pulse will now be here. And notice here between 4 and 5, you've got two different pulses two different pulses in that range simultaneously at the same time at the 3 second mark. So the actual displacement of these bits of string will be equal to the displacement you'd get from this all by itself, plus the displacement you'd get from this all by itself. Well, look at a point right in the middle here. You would get this much displacement if only the triangular pulse were there, and it would get this much displacement if only the funny-shaped right to left pulse were there. So the actual displacement is displacement you'd get from the triangle plus displacement you'd get from the funny shape. The grand total displacement would be like that. And then one more, imagine this point right here. You get just a small displacement. You get a big displacement if only the triangle pulse were passing by that point. And then you get a little displacement if only the strange right to left pulse were there. But since both pulses are there, the actual displacement is just the sum. The sum of this big displacement from the triangle plus this little displacement from the strange shape pulse. So the total displacement would be right there, and you can sort of see the pattern here. The displacement you'd get from the triangle plus the displacement you'd get from the strange shape pulse at every point in this region will just add up to the same total displacement, the actual displacement. So then it looks like whenever the displacement from the triangle is small, the displacement from the funny shape is big enough to make up for that and give the same total displacement all the time. And whenever the displacement from the funny shape is small, the displacement from the triangle pulse is big enough to give the same size displacement everywhere. So what I drew these with dotted lines because what you would actually see at time 3 is the back 2 centimeters of the strange shape pulse, and then just the front, and then just the back centimeter of the triangle pulse. And in this region, you would, since the two pulses overlap in that 1 centimeter space, you see the superposition of the two pulses, the superposition of this piece of the triangle pulse and this piece of the strange shape pulse. So what you actually see is here with the solid line as opposed to the dotted lines. And then one more example, just again, here's two triangle shaped pulses now, but one involves smaller displacements and they're negative. The magnitude of these displacements is about half the magnitude of these displacements. And then the speeds are 10 centimeters per second. This one moves left to right. This one moves right to left at a speed of 10 centimeters per second. So 10 centimeters in a second, so it moves 1 centimeter in a tenth of a second. So after 3/10 of a second, this has moved 3 centimeters. So now it's between 3 and 5. And then this has moved 3 centimeters. So it also is now between 3 and 5. Now the positive pulse and the big positive pulse and the smaller negative pulse overlap, so the actual displacements of the actual displacements that this little bit of string would feel would be the sum of the displacement you'd get from the positive pulse by itself plus the displacement you'd get from the negative pulse by itself. Since this is a negative displacement, the sum is actually, say, this much displacement minus this much displacement, because it's a negative displacement. So something like that. And the displacement right here at 4 would be this much displacement minus this much displacement. And the sum right here at 4.5 would be this much displacement minus this much displacement. So now, these 3 points, connect the dots, and you see that the actual displacement, what you would actually see, what the snapshot would actually look like, I indicate that with the solid line. The solid line is the shape that we actually see, and it's a positive pulse half as large as the big pulse that's moving left to right. Now, when you have two waves moving with the same speed, moving through the same medium, moving in opposite directions, and they're waves created by simple harmonic motion, so that any snapshot would look like a sine or cosine curve. Then, when those two things superpose, you actually get standing waves. We'll talk about this a lot more in class, but here's just a starter for how to think about standing waves. So, imagine that we have a wave traveling left to right, and it looks like this. Traveling left to right. So if we observed, say, this point right here or this point right here, we'd see them at a later moment. We'd see them move to here and then to here. At the same time, we've got another pulse or another wave. A wave with the same speed and same frequency, same wavelength. A wave that is in fact just a reflection of this wave. This wave, maybe the source of this wave was over here, so the wave has a wave velocity going left to right, and then over here the wave will reach a boundary, and whenever a wave reaches some kind of a boundary, it reflects. And so there'll now be two waves on that string, identical in every way except for the direction of their velocity. Since the right to left wave is only a reflection of this left to right wave, both the reflection and the original wave will have the same frequency and period, and they'll have the same speed because they're traveling in the same medium. The only difference is the directions of their velocities. So the other wave, let's say at this point in time, will be the right to left wave. And let's say at this particular moment, the two waves happen to line up perfectly. That will happen from time to time as one wave moves one way and the other wave moves the other way. So I'll try to indicate that with dots instead of dashes. And so that wave will be moving right to left. So if I watch this point on the right to left wave, or watch this point on the right to left wave, I'll see at later times I'll see that this peak has moved this way and this valley has moved this way. But the actual displacement of any piece of mass that's in the path of these two waves is the sum of the displacement you'd get from one plus the displacements you'd get from the other. So what you would actually see is a big displacement here, because in this region the displacement you get from this plus the displacement you get from this is just twice the displacement you get from either one. like that. And now, let's imagine we wait a little while. The left to right wave has moved a little bit, the right to left wave has moved a little bit, so that the two waves don't perfectly line up. Instead, they line up like this. The left to right wave started here with a peak right here, and then behind it was 1/2 of a valley. So all of that has moved, let's say, this far. We take a second snapshot at exactly the right time, so that each wave has moved this far since this earlier snapshot. So this peak will now be here, and this valley will now be here. And the wave that's moving left to right would look like that. Now, what about the right to left wave? The right to left wave. This is a peak in the right to left wave, and it will have moved one step to the left, and then here's a valley in the right to left wave, which will have moved one step to the left. So now that valley will be right here at the second mark, and then this peak in the right to left wave will have moved one step to the left, and then this 0 point, zero displacement point, will have moved one step to the left. So the other wave will now look like that, where that's the valley that's moved from here to here, and then this is the peak that's moved from here to here. But now, again, notice something. The actual displacement of points on the string is just the displacement that you'd get from one wave plus the displacement you get from the other wave. But look at this point. What kind of displacement would it get? Its displacement is the sum of this much positive displacement plus an equal amount of negative displacement, which adds up to 0. And that'll be the same for every other point. The actual displacement right here is this much positive displacement plus an equal amount of negative displacement, and that adds up to 0 as well. So, at this point in time, a snapshot would look like that. Everything is at equilibrium at this moment in time. Call this just T1 and T2. Points on the string are oscillating up and down, so that they're not standing still. It's just that at this moment T2, every oscillating point on the string happens to be at its equilibrium point. Has some velocity, so it's not going to stay at its equilibrium point. Just like any like any oscillating thing, when it comes back to equilibrium during an oscillation, it's got some velocity, so it overshoots the equilibrium point. So we have that. Now, one more. At some time that we'll call T3. Try to line these up so that they're easier to compare. The left to right wave, well, here's the left to right wave. We're keeping track of this point, of that peak and that valley in the left to right wave. And behind this part of the left to right wave is the other half of that valley. So this peak will have moved from here to here, and this valley will have moved from here to here. So this this slope, the left hand of this peak will have moved from here to here, and then the front edge of a valley will have moved from here to here, and then this will have moved from off the diagram into this range. Every piece of the left to right wave will have moved one step. Likewise, every piece in the right to left wave will have moved one step between time 2 and time 3. So this valley has moved from here to here, and this peak has moved from here to here, and this left half of the peak has moved from here to here, and this right half of a valley has moved from here to here, and this left half of the valley has moved from here to here. And similarly, everything else in the right to left wave has moved one step to the left. So now at time 3, just like at time 1, both waves line up so that the actual displacement is really big, twice as big as the displacement you'd get from just one or just the other. For example, the actual displacement of this point is the displacement you'd get from one wave plus the displacement you'd get from the other wave, so twice as big. And here the displacement you get from one wave, the actual displacement would be the displacement you'd get from one wave plus the displacement you'd get from the other wave, twice as big. And likewise here and here. So now let's, with a slightly simpler diagram, less full of all kinds of marks, let's summarize what we've got here. At one time, when we started watching these two waves traveling one to the left and one to the right, what we actually saw, well, what we always see is just the superposition of those two waves. At time 1, what we saw was this. And then at time 2, what we saw was this, everything at equilibrium. And then what we saw at time 3 was this, the same kind of thing as we had at time 1, except flipped upside down. So in other words, remember that every point in the path of these waves is going to oscillate up and down with the same period and frequency as we had at the source. And what's going on here, at time 1, everything had its maximum displacement away from equilibrium, so it was stopped for an instant, and an instant after that it was going to start heading back towards equilibrium. So all these points would start picking up speed and start moving back towards equilibrium. Likewise, all these points would start to pick up speed and head back towards equilibrium, and all these points would pick up speed and start to head back to equilibrium, and eventually everything moves back to equilibrium and arrives at equilibrium at the same time, because everything is oscillating with the same period and frequency. But of course, when any oscillating object gets to equilibrium, it has its maximum speed, so it's not going to stay put at equilibrium, it'll overshoot. In other words, these points have been gaining speed all the way towards equilibrium, so now they've got big velocities. These also have been gaining speed, so they have big velocities the opposite way. These have been gaining speed, so they have big velocities. And then, like any oscillating thing that just overshot equilibrium, now it's moving away from equilibrium, but the restoring force is trying to pull it backwards towards equilibrium. So if the restoring force is pulling backwards, it slows down, eventually comes to a stop, and that's the point where it turns around. That's the point where you're the maximum, where you have the maximum distance away from equilibrium, and that's what happens at time 3. So in other words, all of these oscillating points, oscillating up and down, because there's 2 waves superposing at every point, all these points oscillating up and down and oscillating at the same frequency, they've all gone through half a cycle between time 1 and time 3. Half a period elapsed between time 1, when the snapshot looked like, or time 1 when the snapshot looked like this, and time 3 when the snapshot looked like this. At both time 1 and time 3, everything was at its maximum distance away from equilibrium. Just at time 3, it was on the opposite side from where it was at time 1. So that tells us what the snapshots would actually look like at times other than time 1, time 2, and time 3. We can deduce what other snapshots would look like at other times. It would look something like this. So at time 1, everything looks like this, and at time 3, everything looks like that. So in between, all of these points have been moving back towards equilibrium. All these points have been moving back towards equilibrium, so the shape would look like that. Everything moving back towards equilibrium and getting up to a higher speed the closer it got to equilibrium. So this is the way things look at first, and then here's the way they look at a second time a little bit later, and here's the way they look at a third time when we're actually at equilibrium. But when they're at equilibrium, they have velocity, so they don't stay at equilibrium. These points, remember, had big velocities in the downward direction. So a little after time 3, they'd have displacements like this. And these all have big velocities at time 3. These points all have big velocities in the other direction. So at time 4, a little bit after time 3, they'd look like this. And these points will have been moving this way, and so at time 3 they've got big velocities this way. So at time 4 they'll look like that. And then a little while later they will have gotten to their maximum displacement away from equilibrium on the other side of where they were at time 1. At time 5, everything has displacements like that. So what you actually see in this case is not, you don't actually see a traveling wave moving left to right and another traveling wave moving right to left. All you see are the different points along the medium bouncing up and down. Bouncing up and down between this range of displacements and a half cycle later, this range of displacements. You don't see any waves traveling, you just see things sort of standing in place and then jumping up and down. That's why we call it a standing wave rather than a traveling wave. The usual way we represent a traveling wave is with sort of a double snapshot. A snapshot that shows what the standing wave would look like at one point in time when everything is at its maximum displacement away from equilibrium. And then a snapshot showing what things would look like a half cycle later when everything is at its maximum displacement away from equilibrium on the other side. That represents how things look at one time, and this represents how things look a half cycle later, half a period later. And of course, all the points will oscillate between these. A point right here would oscillate this far on one side and then equally far on the other. This is the maximum distance away from equilibrium on the positive side for a little mass that would ordinarily sit in equilibrium here. And this is the maximum displacement on the negative side for that little bit of mass. But a little bit of mass that would be sitting at equilibrium there goes only this far. That's its maximum displacement on the positive side. And then there's its maximum displacement on the negative side. Much smaller amplitudes. The amplitude of this is only this much smaller than the amplitude with which this point oscillates. And then a point right here would oscillate with an amplitude just slightly smaller than this. It would oscillate between here and here. This is the maximum displacement away from equilibrium for a point that would be sitting right here if it were in equilibrium. And here's the maximum displacement on the other side for that point. So one of the strange things about standing waves is that the actual all these points are oscillating, but they're oscillating with different amplitudes. At one point you get really big amplitudes, and then amplitudes decrease until there's a point with actually zero amplitude, doesn't oscillate at all. And then amplitudes increase up to a maximum, and then amplitudes decrease back to zero. Hang on, let me try to turn that off. So that's a characteristic of a standing wave. Everything oscillates at the same frequency. But different amplitudes. But different amplitudes. And in fact, every once in a while you get a point with zero amplitude, in other words, no oscillation at all. Those are called nodes. And then in between nodes, you get the points of maximum amplitude. Those are called antinodes. One important thing about the nodes, and this is true for every standing wave ever, the distance between nodes is half a wavelength. The wavelength of the traveling waves that superposed to cause the standing wave. Distance between nodes is half a wavelength, or equivalently, distance between antinodes is half a wavelength. And you can use that to actually compare different wavelengths on different strings, setting up different standing waves. For example, let's say the whole length of this string is 30 centimeters. Well, within that string length, you've got 1, 2, 3, 4 half wavelengths, because node to node is half a wavelength. Node to node, 1 half wavelength. To the next node, 2 half wavelengths. To the next node, 3. To the next node, 4 half wavelengths. So there are actually 4 half wavelengths in the entire string length. And so you can just do the algebra, and that will tell you that in this case the wavelength for the traveling waves that caused this particular standing wave would be 15 centimeters. Let's say same string, so a length of 30 centimeters, but in this case 1, 2, 3, 4, 5 half wavelengths fit in the entire string length. Node to node is half a wavelength, so 5 half wavelengths fit in the entire string length of 30 centimeters. So do the algebra, and in this case, you find that the wavelength is 12 centimeters. And then more practice, much more thought about this when we get to class.